So this is Lab 11, The Falling Slinky by Pouria Hosseini, section M06. And the main problem in question in this lab was what happens when you drop a slinky? Will the top go down to the bottom? Will the bottom go up to the top? Will both ends move and meet somewhere in the middle? Or will both ends move together and fall down? So I used the momentum principle to model this motion and try to find the answer. So there was a video made to show what happens if the slinky is dropped, and I extracted the data from this video in Tracker. And the first thing I did was I extracted the position of the top of the slinky as it moves down. And also the origin is where the professor lets go of the spring at the beginning, and the video was calibrated using the length of a tennis ball, which was found to be 0.0635 meters. I also did the same video and tracked the motion of the ball. So you can see it's relatively still throughout the video. And I extracted both of these data and put them into Excel and tried to compare them with the model, which I'll show you in a second. So I modeled the motion that I tried to model the same motion that I extracted from Tracker, and in order to do that, I just took the Lab 8 motion, spring motion, and I just edited it a little bit to include motion with the spring. So I calculated the position of the spring using the momentum principle, as you can see here. And then I also graphed and recorded the data of the spring position and ball position. So if I run it here, you'll see that the spring will start to move, but the ball will remain stationary. So this first graph here is showing the position of the ball. And the force that is acting on the ball. This force is the force of gravity plus the force of the spring. And as you can see, even though there's a force acting on the ball, there is no motion in the ball. And this graph right here shows the force of gravity and the force of the spring, and then the blue line is both forces added together. So as you can see, there is a force over time, but the ball still remains stationary. So here I've plotted the position of the ball. And here you can see the blue line is the model and the orange line is the experimental. They're different as far as the height goes because I didn't know the length of the spring accurately, so I just used the length of the spring that we used in part 8 of the lab. So that's unimportant, however, but as you can see in both cases the ball remains stationary. Here's the position of the spring, however, and as you can see in both cases the position of the spring rapidly decreases exponentially, and again there's some difference because it's not the exact same situation, because I didn't know the spring constant for the slinky or the length of the slinky or the mass of the slinky, so I used the data that we had from Lab 8. So here we go. As you can see, the answer is that the top of the slinky moves down to the bottom, and almost magically the bottom of the slinky does not move at all until the top of the slinky reaches it. The explanation given for this is that even though the forces are unequal, it takes some time for that motion to propagate at the speed of sound to the bottom of the slinky, and so by the time that information gets to the bottom of the slinky and the slinky almost realizes that the forces are unequal, it takes a small amount of time, and that's why there's a delay in the difference in force and in the motion of the slinky. So thank you for listening. Have a nice day.